Okay, so in the last video, we studied derivatives of parametric curves, and now it's time to look at integrals of parametric curves. So derivatives of parametric curves really rehashed units 2 and 3, the applications of differentiation and differentiation rules, and we were basically able to expand that to parametric equations. So now the task for us is to expand units 4, 5, 6, and 7 to look at how we can apply what we've learned about integrals to parametric curves. And as you can imagine, it's a very generalized method, and it doesn't take too long to go over. All of the rules will just be reapplied to a different type of family of curves. All right, anyways, let's look at some integrals of parametric curves. So here's a definition for you. So to find an area under a parametric curve, we'd normally try to find the integral of y with respect to x, right? So that's what we call our area. However, we have the integral of y of t dx of t. So actually what we need to do is we need to be a little bit more careful with how we define things. So we know that y equals g of t. Then we can write dx equal to f prime of t, because we know x is equal to f of t. So if we take dx, we get f prime of t dt. So then we can plug this into our integral. We get the area under the curve between the x-axis and the curve is equal to the integral between a and b, or starting and ending points, of g of t times f prime of t dt. All right, so that's how we do those integrals. So now let's cover an example, see how we actually apply this. So let's find one area under one cycle of the cycloid. So the cycloid is a parametric equation that looks kind of funky. It's like just a bunch of curves and a bunch of cycles. It's what the circle's perimeter traces out. If you put a point on the edge of a circle, that's what it traces out as it rolls along. Anyways, it's parameterized by this set of equations. X of theta is equal to r times theta minus sine of theta, and y of theta is equal to r times 1 minus cosine of theta. Okay, so the way that we do this, if you remember, the integral is going to be the integral of y of t dx of t dt. So, we don't need the dt there because that comes in the dx of t. Okay, anyways, what we get is we get the integral from 0 to 2 pi r of y dx, and then we simplify that and we plug in everything. We need to take the derivative of x of t, or x of theta, to put into our differential, because we've got y here, but we need x here, or x prime there. So x prime, we have x of theta is equal to r times theta minus sine of theta. Then x prime is going to be r times 1 minus cosine of theta. Okay, so this actually works out really nice because we just can pull out the r squared, then we get the integral between 0 and 2 pi, and then we FOIL out this expression. We got 1 minus 2 cosine theta plus cosine squared of theta d theta. Now, if we remember how to tackle this integral, we can do the sum rule. We can separate everything. Both of the first ones look fine. The second one might be a little bit messy, but if we remember the rule, if we have cosine squared of theta, we can use the double angle rule, and that makes things a little bit easier for us. So what we get is we get the antiderivative. So we get r squared times 3/2 theta minus 2 sine of theta plus 1/4 sine 2 theta. And that's evaluated between 0 and 2 pi. Obviously, the sine function cancels out at 0. So does the first monomial. So we get only everything evaluated at 2 pi, which gives us 3 pi r squared. That's how we find the area under a polar curve. But if you remember, that wasn't the only stuff that we were doing in integration. We also discussed arc length. And arc length is particularly important with parametric equations because we want to know how far our curve goes, how long our curve is. Usually that's even more important than areas. So of course, what you would imagine is if I have a curve like that, I'm I might want to find a little change in y and a little change in x. Now this is a little bit different because these are now both functions of t. So our old equation for arc length is the area between a and b of the square root of 1 plus y prime squared dx. But now these are both functions of t. This can no longer be 1 because we might be moving different x values. So we need to change this. So we get the length is equal to the integral between a and b of the square root of x prime squared plus y prime squared dt. And x prime and y prime are all obviously functions of t. Okay, so why don't we use this to verify a very nice problem. But first, I just want to preface this by saying with this formula and with the formula we saw earlier, we can apply all of the disk and shell methods, the surface area, surface of revolution, disk method, shell method, what have you. We can apply all of that with these integrals. It's just a generalization that we can use if we want to rotate these guys around or whatnot. Anyways, let's find an expression for the parameter of a circle. For the parameterization of a circle, we want to find the perimeter. So anyways, I think this is spelled wrong, parameter. X of t is equal to cosine of t, and y of t is equal to sine of t. In this case, we have t going between 0 and have 0 to 2 pi for one about around the unit circle. We want to find the arc length. So we find both of our derivatives, x prime of t squared is equal to sine squared of t, y prime of t squared is equal to cosine squared of t. And I plug this into our integral. We get L is equal to the integral between 0 and 2 pi, square root of sine 2t, plus cosine squared t dt, which is equal to the integral between 0 and 2 pi of dt, because this, of course, becomes 1. And then we just get 2 pi, and that's the expected result because it's a circle of radius 1. 2 pi r is the formula, so we get 2 pi. Okay, anyways, now if I were to change the frequency of these cosine and sine functions, so I were to go to cosine of 2t and sine of 2t, well, this would mean that for this means that we are rotating about the unit circle twice as fast. So if I had t going between 0 and 2 pi, then we would actually rotate around the unit circle 2 times, so we'd get 4 pi for our arc length. All right, anyways, that's how we do integrals with parametric equations. In the next video, we're going to talk about polar coordinates and polar curves and how we can do calculus with those guys as well. All right, we'll see you in the next one. Bye.